Welcome. Today we will visualize the water overflow problem using dynamic programming. Imagine a pyramid of glasses. The most important rule is simple. Each glass has a capacity of exactly 1 unit. So what happens if we pour more water? If a glass receives X units, it keeps 1 unit for itself. The excess water, which is x minus 1, overflows. This overflow is split equally, half goes to the bottom left and half goes to the bottom right. Physically, this looks like a triangle, but mathematically, we map this as a coordinate system.
Each glass has an address, row I and column J. Our goal is to calculate how much water ends up in a specific glass after pouring K units at the top. We cannot calculate a glass's water level directly. Why? Because every glass depends on the overflow from the ones above it. We must simulate the flow level by level from top to bottom. Let's simulate with an example. We pour 5 units into the top glass. It stays full with 1 unit and 4 units overflow. That means 2 units flow to the left and 2 units flow to the right.
Now, pay attention to the middle glass in the third row. This is the key part of dynamic programming. Unlike the edge glasses, this one receives overflow from two parents, both the top left and the top right. The water accumulates here before overflowing further down. Here is the algorithm in action. For every glass, we check, is the water greater than 1? If yes, we keep 1. Calculate the overflow and add it to the specific glasses in the next row. Row I plus 1, column J, and column J plus 1.
Finally, let's talk about efficiency. To find the answer, we must process every glass in the pyramid up to our target row. This corresponds to the area of the triangle. Therefore, the time complexity is O r squared. For space complexity, we have two approaches. In the first approach, we can store the entire matrix in memory. This costs O r squared space, which includes a lot of wasted empty area. In the second approach, notice that we only need data from the previous row. By using a single array and updating it on the fly, we can optimize the storage to just OR. This makes our algorithm much more memory efficient. And that is how we solve the water overflow problem efficiently. Thanks for watching.